Okay, so we're on page 360. This is 7-1. And we were talking about polygons. We spent a lot of time talking about triangles already this year. We're getting away from triangles. The stuff we're talking about still applies to triangles, but we're going to get away from those and we're going to look at other polygons now. We're going to look at quadrilaterals, pentagons, hexagons, dodecagons, 14gons, right? All of them. We already learned the names of these back in a different chapter. Hopefully you remember those. If you don't, you do have them written down somewhere. Make sure that we know. First thing we're talking about is this term diagonal, and I know I've used it before in class, and I've had some questions throughout the year because people tend to think that a diagonal has to be in that direction, right? We think of a diagonal, we think of that. It doesn't necessarily have to be, right? Here's a diagonal that is horizontal. A diagonal just means a segment that connects two non-consecutive vertices. So it's a line that goes across our figure and connects two vertices. So these two would be considered diagonals. Okay, so that's any time we're connecting two non-consecutive vertices.
Would that be a pentagon?
That is a pentagon. Yes. Yep. It's 5 sides. Okay. So we've got our diagonals, our definition of diagonal. Now, what we're going to talk about first, we're going to talk about the inside of these polygons first. Okay, the inside. We already know, because of triangle sum theorem, how many degrees are in a triangle? 180. Okay, 180 degrees. It's a quadrilateral, right? 4-sided figure, quadrilateral. Less than how many degrees?
360.
360. Now let's take a look at why or how we know it's 360, because that's going to help us moving on. If we draw in all the diagonals from one point. So really here we just have one diagonal that we can draw in from one point. This splits it up into two triangles. So if we use that triangle sum theorem, I know this has 180, this has 180. We can add those two together to get 360. Because we're looking here, we got two triangles, right? Two triangles equals 360. We look at a pentagon, and it doesn't have to be, you know, all sides being the same or anything like that, just any pentagon. We draw in those diagonals, we now have three triangles. So we have three triangles, which means I can do 3 times 180 to get my 540 degrees that are inside a pentagon.
So every time you add a side, you add a new triangle, so you add 180 degrees.
Sure, yes. So, yeah, Bryce?
Do you do the amount of sides times 180?
Close, but it's not the number of sides, right? Because here we've got 4 sides, but only 2 triangles, right? Here I've got 5 sides, only 3 triangles. Brandon, what's the rule?
Sides minus 2 times 180.
Sides minus 2 times 180. So we're going to use n as the number of sides. N is the number of sides. And our rule here is n minus 2 times 180. Because that n minus 2 is going to tell you how many triangles we have in the figure. And then we can times it by 180 because of triangle sum. We're going to get that total number of degrees inside of a polygon. Okay, total number of degrees inside of a polygon here. And that's our first theorem. So if you wrote down the theorems, this is the polygon interior angles theorem. Okay, they put a little more words into it. But that's what they're saying, right? N minus 2 times 180 gives us the sum of the interior angles. One thing to notice, it does have to be a convex polygon. Remember, convex means everything's pushed out. Nothing is caved in. So this only works with convex, where all of our vertices are out. Okay? But it's going to work for any convex polygon. Yeah.
Do we need our orange sheet still?
You're still going to use them. Second half of the year, we're going to use more of the other side now, with the formulas and everything like that. Okay. Any questions on this one?
it was, had six sides or six angles like that one, it would be 723.
Because then it would be 6 minus 2 is 4. 4 times 180 gives us that 720. Yep. Yep. And so we can do that, right? And instead of having to count and add 180 every time, if I told you that it was a dodecagon, how many sides does a dodecagon have?
8.
12. 12 sides, dodecagon. Deca meaning 10, right? And do meaning 2. Dodeca is 12. So dodecagon, 12 sides. We would do 12 minus 2 is 10. 10 times 180. There's 1,800 degrees inside of a dodecagon. Okay. So we've got that. We're going to use that to be able to solve problems, right? They might give you something simply like, all right, here's a figure, how many degrees are on the inside, right? You might be able to say that. You just got to count the sides, use the formula. But beyond that, you're going to see stuff like we did with the triangle sum theorem, only now we have to figure out how many degrees it's going to equal first. Right? Now, this has 4 sides. How many degrees does a 4-sided figure have? 360. We know that. That's actually our corollary. Remember, corollary is just a branch off of the original. It's just an extension of the original theorem. So this is saying, yeah, we can still do that n minus 2 times 180, but we should just know that a quadrilateral has 360, right? That's what this corollary is telling us. It's quadrilateral, 360 degrees. So we can take the fact that a quadrilateral has 360 degrees and then set up our equation to be able to solve something like this. Right? We would add all 4 of those up, set it equal to 360, and then solve for x. Right? Yes, Tyler?
That'd be 72.
I have no idea.
Because 121 plus 59 is 180, so the other one has to be 180.
Sure. There you go. Right? And we can set up that equation. We can solve for it. Okay? Good deal. So that is our use of the polygon interior angles theorem. The good news about the second half of the year, there's not a lot of proofs. Right? Most of the chapters, you're not going to see any proofs. I think chapter 7, we might still see some because it's on that orange sheet, right? But once we get past chapter 7, we're pretty much done with proofs until the final exam. Right? 12 chapters. But a couple of them are pretty short. I mean, you look at chapter 8, there's only 4 sections. Chapter 12, we're only going to do 3 sections out of it. So
Where's 9?
this is
So then
going to,
how do
they're
we
just not
do
up there yet.
Do we even do a quiz for
We'll
it?
either do a quiz or a test, but not both. for those.
Not if we just do a quiz.
Well, I forget which chapter it is. One chapter I'll only do a quiz, one of those I'll only do a test. So even out.
The homework for 12.1 should be a quiz.
Just the homework,
Yeah,
call that a quiz.
Well,
I don't know, you guys don't always get 100% on homework, so
I am.
probably not a great idea. All right, anyway, moving on. So we got those corollaries, or that corollary saying that's 360. All right, moving on. We got to look at this idea of a regular polygon, and the name is deceiving because when you think of something's regular, you think it's just average. It's just there's nothing special about it, right? But a regular polygon is a very specific, special type of polygon. Okay, a regular polygon is an equilateral and equiangular polygon. Now, with a triangle, we said equilateral means equiangular, right? And vice versa. Not necessarily true with any other polygon. You see it here. We got hexagons here. This one is equilateral. All the sides are the same, but the angles aren't. Here, all the angles are the same, but the sides are not. So triangle is the only figure where that equilateral means equiangular thing applies. That's the only time where you can go back and forth for sure. In terms of our other polygons, if it's both equilateral and equiangular, that's what we consider a regular polygon. Okay, a regular polygon, both equilateral and equiangular. We see it here with our hexagon.
Isn't that just
The definition of a square,
It's equiangular and equilateral.
definition of a square, it's a quadrilateral with 4 right angles and 4 congruent sides. So yes, but not in those words.
So if you ever see a square, you can always say it's like the.
We know if we have a regular quadrilateral, then it's a square. Yes. Okay. All right. So we got regular things, and we're going to use the fact that figures are regular later on when we're trying to solve some problems. Just remember, if it's regular, that means all the sides are the same, all the angles are the same. All right, one type of problem that we're going to see is going to be something like this, and this is going to go along with that first theorem that we looked at. But we're looking for, well, 2 things. First of all, is this regular? And then we're looking for the measures of C and E. Okay. First of all, is this regular?
No.
No, it's not regular, right? You've got 3 right angles, you got 2 obtuse angles. We know they're not the same. It's not regular. And the sides might be the same. They're not, but they could be, right? But the angles for sure are not. Find the measures of C and E. I want you to go ahead and do that. I want you to figure out what the angles C and E are going to be. And keep it to yourself until we're ready to talk about it. First thing we have to do is we have to figure out how many total degrees there are, right? How many total degrees here?
540.
540. And we knew that because we wrote it on the board before, but also we could do the n minus 2 times 180. So there's 540 total. We know there's 3 90-degree angles, so we can say 90 plus 90 plus 90. And then what are we going to do with the other 2 angles here? Hold.
You subtract the 93 times from 540 and then divide that by 2.
Yeah, because we know E and C have to be the same, right? So if we're going to set up our actual equation, we would say it's plus x, because there's 2 of the same number left. So we take that, we know that's 270, we subtract it. So we've got 2x is equal to 270, because that's what we get when we do 540 minus 270. We divide it, of course, x is equal to 135. So anytime you have this type of problem, and you're going to see it not just with 90-degree angles, but other angles. If you have 2 that are the same, and that's what you're looking for, just use a variable. Call them x. Just make sure you're adding as many as there are into that equation. All right. Good deal. So that would be something, we're not going to do this one, but that would be something like this, right? Same idea. Instead of the 90, 90, 90, we'd have 93, 156, 85. And we'd sort it all. Okay. All right. So that's the interior. Any questions on the interior of polygon? So now we're going exterior. Okay, exterior. Exterior is even easier. Okay, exterior is even easier. Let's look at a couple examples here. See if we can't create this this idea. Let's say that this is, for sake of ease, equilateral, equiangular, right? We're talking about exterior angles. How many degrees is that exterior angle? 120. We did that in the warm-up, right? That's 120. So if I did one exterior angle on every side, what would that add up to? 360, right? There's 120 there, 120 there, 120 there. 360. Okay, there you go. Let's think of a rectangle. I do one exterior angle at each side. Remember, exterior angles doesn't have to face the same way, doesn't have to be a pattern, because it doesn't matter which side you extend, they're gonna be the same. We talked about that before, how they're vertical angles. So as long as you have one at each vertex, doesn't matter. I've got a weird table looking thing here, it doesn't matter. But how many degrees are each one of these? 90. 90, 90, 90, 90, what does that add up to? 360. Our rule for exterior angles is the sum of the exterior angles will always equal 360. Doesn't matter what type of figure. The exterior angles, if you take one at each vertex, will always add up to 360. That's our last theorem. Volume exterior angle theorem. Always equals 360. So much easier. We don't have to do anything else. There's no formula to find it. It's 360 every single time.
Wait, could we just do like could we do where it's n, so n is the number of sides minus 3. Why would you do that?
Why are you trying to make it harder than just it's 360? Right? Yeah, I'm sure you could come up with some long thing, but it's 360.
Are we still taking pictures of our homework or turning it in?
No, we're gonna turn it in since we're all in person. So, yep, we'll tear it out tomorrow. Turn it. All right. So it is equal to 360, which means we're going to see the same sorts of questions that we saw with the interior, but with the exterior now. Just knowing that we're going to set up the equation, it's always going to equal 360. Why don't you go ahead and solve for the value of x? Here, solve for the value of x, please. Write the equation and then figure it out. What is this?
60.
68. Okay, so there's our equation, right? We add them all up, set it equal to 360, combine like terms, solve the simple equation, we get 68. There we go. Okay, so pretty straightforward for the exterior. Any questions on that? All right, now one more question to show you. Previously shown is shaped like a regular dodecagon. We already said that's 12, right? We want to find the measure of each interior and the measure of each exterior. Go ahead. Oh, yeah. If you're gonna find each individual angle, you gotta find the sum of the angles first, right?
Oh.
Find the sum of the angles, the total of the angles, and then we can figure out what each individual one is.
That's easy.
Okay, how many degrees for each interior angle here? Each interior angle, right?
150.
150. It is 150 degrees. Talk about how to get there, right? We know there's 12 sides. 12 minus 2 times 180. We already said that's 10 times 180, which is 1800. Now we know each angle is going to be the same, so we can take that 1800, divide it by 12, and get our 150 degrees. The common mistake, and I don't understand it, I'll never understand it, but people do it, is they'll go through all of this, they'll get this 1800, and then they'll decide to divide it by 10 instead of 12. And they get 180 degrees, and they're like, well, the interior angle is 180 degrees. It can't be 180 degrees, right? That's a straight angle. We can't do that. So just make sure you're dividing by the original number of sides there to get that 150. All right, how about for B? What's the measure of our exterior here? Jordan? 30. 30. It is 30. 360 divided by 12 gives us 30. What do we notice about those two numbers?
The exterior.
What's, hold on, raise your hand. Got other people in here too. Here? Okay, that's just in this case, that's a coincidence, but that is true. When we multiply by 5, we get there. What else can we say about these? Brandon? They're a linear pair, right? That's always going to be true. It's always going to be a linear pair. Because if I extend it out to an exterior angle, I've got the interior here, I've got the exterior here, it's always going to be a linear pair. So when you're talking about a regular polygon, the interior, the exterior, always are going to add up to 180. They're always supplementary. Which means to me, if I hear that, and I look at the work needed for both of these, which one am I going to do first? I'm going to do the exterior first. I'm going to do 360 divided by how many sides I have, get that, and then just subtract it from 180 and get this one. I don't even have to worry about the n minus 2 stuff. Right? So that's another way that we can get there is find the exterior first, the easier one, subtract it from 180, and get that one. Any questions about it? Okay, you guys stuff copy down again tonight? Okay, I think one vocab word, like 4 theorems, something like that. Okay, other than that, we're working on the homework. We are turning it in tomorrow. Okay, so do it on a page that you can tear out tomorrow.
That's next